Hello guys, welcome to my YouTube channel. So today we are going to have a brief description of how multiple CSTRs work in series. So starting from the basic material balance equation. So for the nth steady state CSTF, the material balance for the microorganisms or for the biomass, because here we are interested in the growth of the microorganism, which we other called as growth of the biomass. So it can be written as F Cx minus 1 minus Cxn plus Vn Rxn equal to 0. So how we are getting this equation, I have explained it in my previous lectures on bioreactors. If you, I suggest you that you go and watch my other lectures on CSTRs, on PFRs, on fed batch reactors, and then you come to this lecture. You will easily understand how we are getting this equation by mass balance. Okay, so this is a series of reactors, CSTR reactors in series that has been shown. So each reactor is having an inlet stream with a flow rate of F, and inlet stream we are saying that it has its own cell concentration, which is CXI, and substrate concentration that is entering, which is CSI, in a particular reactor of volume V1. Okay, so from this reactor again some outlet stream is growing, which is again entering into the second reactor, and this outlet stream has a cell biomass concentration of Cx1 and cell substrate concentration of Cs1. So likewise from first to second, second to third, third to fourth, likewise in series, the outlet stream of one CSTR acts as the inlet stream of the other CSTR. So likewise we go to the nth reactor. So this is the nth reactor with a volume Vn, and it has an inlet flow stream from n-1th reactor, whose cell concentration is Cxn-1 and substrate concentration is Csn-1, and the outlet stream has a cell concentration of Cxn and substrate concentration of Csn. Now I will tell you one thing which is very important. So it is said that two CSTRs can perform better than a single CSTR because the first reactor operates at a higher concentration than the second, resulting in a great rate and conversion. So if you have a two CSTRs, it is always preferred because there is more like conversion rate, and the first reactor can operate at a higher concentration. So likewise if you have multiple CSTRs, then that is always preferred over one CSTR. So what are the advantages if you operate this CSTRs? We will come that later. So this is the mass balance equation that we had been talking about. So I'll just explain it quickly for those who haven't watched my previous lectures, so how we are getting this. So the basic equation for mass balance stands at input minus output plus generation of anything minus consumption of that thing. Okay, so input of a particular thing in a bioreactor, suppose we are talking about the input stream, okay, which has having a inlet biomass concentration of Cxi. Okay, so then output will be the output stream of that particular biomass concentration, generation will be that biomass, and consumption will be that particular biomass. So here we talk about everything in mass balance or mole balance. Okay, so suppose you are having, I'm not going to the like suppose you are having the inlet biomass concentration of xi, okay, or say xn-1. Okay, so this is a concentration, cell concentration, which is in grams per liter. Okay, so we are doing what? We are doing mole balance. So we have to get, or we are doing mass balance, for example. So suppose we are doing mass balance here. We are interested in mass balance. Then what should we multiply with this grams per liter to get something in terms of rate of like generation of biomass, something in grams per unit time, okay, grams per second, like that. So what should we get? We should multiply something with liters per second. Okay, So if you multiply liters per second with grams per liter, what we get is the grams per second. Okay, so this is actually in the original mass balance equation, we write it as rate of change of mass. Okay, dmdt, and at steady state this dmdt is taken to be 0. So right, that's why this is a steady state, right hand side stands at 0. So because cell concentration is grams per liter and we have to multiply it with something in liters per second so that we get the final unit in grams per second, so we multiply this with the flow rate of that particular stream. So F, flow rate. So because it is entering, so it is positive, and by convention something is leaving, then it is negative. So again we multiply the outlet biomass concentration. If the outlet biomass concentration is xn, we multiply it by flow rate so that the unit remains constant. So fxn minus 1 minus fxn. Okay, this is the input, this is the output, plus generation of the biomass. So we consider the generation rate of generation of the biomass to be depicted by Rxn. Okay, now what is the unit of this rate? So its unit stands at grams per liter second. Okay, grams per liter second. Now we have to make this unit in grams per second. So what do we have to do? We have to multiply it with the volume. Okay, if we multiply it by liter, that means the volume, we get this unit. So we multiply it by the volume of the reactor. So this is the generation, and we consider there is no consumption of biomass, so it is 0. Okay, so this is your input. This is your input of the biomass. This is your output of the biomass. Okay, and this is your generation of the biomass. Okay, this is your generation of the biomass, and this is your consumption, which is, we are considering that there is no consumption right now. So this is the master equation of mass balance. Okay, so this is the master equation of mass balance, and this, from here we get this equation. So that's why this equation is written. Now where I will explain this rate equation, that you find that rate expression. So this rate expression is taken to be the monad model. So Rxn is mu max, which is the maximum specific growth rate, into the concentration of the substrate in the outlet stream multiplied by the concentration of the biomass in the outlet stream divided by the monod constant Ks plus concentration of substrate in the outlet stream. Okay, and the growth yield or the yield coefficient, which I have already talked about in my previous lectures also. So YXS is written as the final substrate concentration, final biomass concentration minus initial biomass concentration divided by the initial substrate concentration minus the final substrate concentration. Okay, so here we can write it as del x by minus del x by minus del s. Okay, these things are already discussed. Now, so if we solve these equations, we can get the dilution rate with the known cell concentration, vice versa. Now, as I had been talking about, what are the advantages of operating multiple CSTRs? First is, of course, the better performance. And because two small CSTRs can perform better than one large CSTR, because the reaction rate in a single CSTR is usually low due to a small reactant concentration. And another point is better resistance time. So a series of CSTRs can provide better control over residence time, as each module doesn't necessarily flow through the reactor at the same rate. But there are certain disadvantages also. So what is the disadvantage? If you are operating multiple CSTRs in series, and if one circuit fails, the entire process stops. And if you are like putting more components in series, the resistance also increases. Anyways, coming back to our lecture, So if you remember this was our equation, mass balance equation for the CSTRs. Okay, now from this equation we assume that there is the inlet stream is sterile. Okay, this we are assuming. So in the first reactor, so this is your first reactor, this is your second reactor. So the inlet stream which is entering here in the first reactor, we assume it is to be sterile. So there is no initial biomass concentration in this sterile feed, okay, which is entering the first reactor. But the outlet stream which is leaving the first reactor and entering the second reactor, there is a particular biomass concentration in this outlet stream, not to be confused between the two. Okay, inlet stream in the first reactor, it is free, it is sterile, there is no biomass concentration. But the inlet stream which is entering the second reactor, which is actually the outlet stream of the first reactor, that there we have some biomass concentration. Okay, so if we assume it, then from this equation we can easily get this. So dilution rate is actually defined as the flow rate divided by the volume of the reactor. So it is Rx1 by Cx1. Okay, how we are getting this? Let's see. So suppose the inlet biomass concentration of the first reactor, which is in this case, okay, so if we talk about this, so inlet stream is actually is a 0, and so from this equation we can easily figure out. Suppose I'm writing here, so what was our expression? So f of x minus 1 minus of x n, okay, plus of vn rxn, okay, is equal to 0. So if we assume the sterile feed, what happens? So there is no biomass concentration in the inlet stream, so this becomes 0. So here we get as fxn is equal to vn rxn. Yes or no? And from here we can, by transposition, we can bring this. Okay, so dilution rate is defined as the flow rate divided by the volume of the reactor, which is Rxn by the concentration of the biomass. And what is Rxn? Again, it is put in terms of monod equation. Okay, so for here Rxn we can substitute the monodic expression. Okay, so it is actually the form of y equal to mx. This d1 is equal to rx1 by cx1. This is actually the form of y equal to mx. What is rx1? Is d1 into cx1. So if we compare this, okay, so if we write it as like this, rx1 is equal to d of d1 into cx1, okay, cx1. So if we compare this and plot rx1 on the y axis and cx1 on the x axis, what is the value of the slope? It is d1. Okay, so if we can plot the rate on the y axis and the biomass concentration in outlet stream in the x axis, then the slope that we get is will be the dilution rate. Okay, and if we note this flow rate, okay, if we will get the value of the dilution rate from the slope. If we note get the flow rate, we can easily calculate the volume of that reactor. Okay, so for similarly for the second fermenter, here we are not assuming the inlet stream in the second fermenter is sterile. So here we will get this d2 is equal to f by v2 is equal to rx2 by cx2 minus of cx1. Okay, this we will get. Again here also, this if we plot this, if we plot the slope of the line connecting cx1 comma 0 and cx1 comma rx1, the slope of the line will give the value of d2. So here, as you can see, this is a pictorial graph manner. So this is rx1 on the y-axis and cx1 is shown on the x-axis, and this is the curve that you are getting. So if you are taking the slope of this curve, okay, you are taking the slope of this curve, so this slope of this curve will give you the dilution rate. and if you know the flow rate, you will calculate the volume of this reactor. Okay. Similarly, for the two reactors operating in series, if for the second reactor also you will get one curve, and if you calculate the slope of this curve, you will get the value of d2. Okay, you will get the slope as d2. Okay, and from there you can calculate the volume of the second reactor, right? So we will discuss it in more detail when we solve problems, then you will easily understand. But one thing you should know, so the slope, okay, so this is the curve that you are getting, and this is the cx1 comma 0 point, cx1 comma 0 point, and there is another point which is cx1 comma rx1. So this point is the cx1 comma rx1. Okay, so likewise we can calculate the slope. So therefore, by knowing the dilution rate of each fermenter, you can estimate the cell concentration or the volume also, and vice versa.